There we go. Now we have audio. All right. Let me think about how to do this intro right now. I gotta think. What is I'm just trying to think of like what is a decent intro. So, what up nerds? Welcome to the stream. Today we are going to be exploring the build of an AC to DC converter that is alternating current to direct current. We're going to utilize components such as diodes to form a full bridge wave rectifier. We're going to use a capacitor to limit our ripple voltage. And we're going to use a voltage regulator to ensure that our output is constant. Alright, so without further ado, one more thing I wanted to say is that like the video and subscribe or follow depending on the platform. Let's do some science, let's do some physics, let's do some engineering, okay? We're going to cover it all. Alright, so to start off, let's get straight into the theory of things. Alright, we're going to theorize our circuit first. We're going to draw it out, put our components on paper and things like this, and then we're going to go ahead and start putting components into a breadboard. And we're actually going to prototype. I guess I don't know if you really consider it that, but that's what we're going to call it. Alright, let me check the live video real quick. Just do this little. And we're actually going to prototype. I guess I don't know if you really consider it that, but. Alright, that sounds fantastic. That sounds great. I'm going to like my own shit. Alright, here we are. Alright, so let's get straight into it. Let's start drawing out. So, okay, here I'm just going to show you first. Alright, this is my transformer, okay? And I already have a full bridge wave rectifier, right? This is what we call it, right? A full bridge wave rectifier. Full bridge wave rectifier. I just want to make sure I'm saying all those terms in the correct order. Okay, see, I already messed up. It's a full wave bridge rectifier. Okay, here, let me hop over to my other screen. Okay, full wave rectifier and bridge rectifier. Full wave rectifier, bridge rectifier. What, same thing? So we're going to do a full wave rectifier, which consists of these 4 diodes here. I'm not even going to show you because we're going to do it here. Alright, but this is my transformer. This is my full wave rectifier right here, okay? So I already have these 2 components in place. Alright, so we're going to draw that out. Okay, along with that, in series with this transformer, and then in series, or well, I guess it'd be in series and parallel, this in parallel with that full rectifier, we also have a fuse in here, right? A safety mechanism to ensure that we don't damage any of our other components with too great of a current. If the current exceeds the rating of the fuse, then it's going to burn and disconnect the entirety of the circuit. Okay, so that's the purpose of a fuse. And then also we have a switch here, on-off switch. Okay, so that's our transformer. That's our full wave rectifier, which on the output of the rectifier, we're going to have some DC current with some crazy ripple in it, right? I'll show you what that looks like. I'll draw out the wave function and everything, okay? Alright, so we just have our input here. Okay, actually we're going to have, before we get into the primary of the coil, we have our fuse, which is going to look something like this. Alright, so that's a little symbol for the fuse. We're going to have that, and then that's going to be to the input, or well, the high side of our transformer, because it's a step-down transformer. Therefore, we're going to model it with multiple coils on this side, like a lot of them, okay? These 2 lines are going to represent our iron core. This is necessary to a transformer. You need the iron core. And then this side is going to have less coils in its symbolic representation for the purpose of expressing that it's a step-down transformer. Our output has less coils, less woundings, because it's lower voltage. Okay, so along with this, we're going to have that. Actually, we're just going to put this switch on this side, which is okay. You could have either or, because it's alternating current, and so having especially these two components, the switch and the fuse, it's not very particular in which side of the circuit you put it on. As far as like, if we consider this positive and this negative, and then you have some ground here, right? Because the alternating current is high here, low here, high here, low here. That's the way the alternating current operates. So it doesn't really matter whether you have the switch on this side or that side, or the fuse on this side or that side. Okay, if we could even have the switch and the fuse in series, it's possible. So right here, we're gonna model as this is the outlet. Okay, this is the outlet of my apartment right now. So that's what that is. AC, we'll just put like 60 volts, right? Or not 60, 120 volts. This is what we're working with. Okay, so 120 volts at 60 hertz because I'm in the US. 60 hertz AC. Okay, so 120 volts AC at 60 hertz. I zoomed out so that we would be able to see the transformer and everything, but as of right now I need to zoom back in. It's just a little too far away. So let's go ahead and do that. There, now we can see things a little bit better. Alright, fantastic. Okay, so this is what the transformer is going to look like. So we have the input from the outlet into our transformer here with a safety mechanism and an on-off switch. Okay, the safety mechanism being the fuse. Alright, so we come to our transformer here, and then we step down the voltage to, so we have like 120 volts, right? 120 volts. We're going to step it down to, I've measured it before. We'll pull another measurement, but I think it's approximately 18 volts. So we'll just represent it as that. So a step down from 120 volts to 18 volts. Mind you, this is still AC. Here, let me give it some space. Mind you, this is still AC. 120 volts AC. 120 volt, or, oh man, forgive me. 18 volts AC. Okay, and then now we're going to go to the full wave rectifier. Okay, so this is going to look like this. Draw like a nice diamond, looking real beautiful. Okay. And then it's gonna look like this. That's one diode. Here's another diode. Pay attention to the orientation of the diodes. You know, this is our anode. Wait, yeah, right, because the cathode. Here, let me just double check one more thing. Diode, anode, cathode. I just gotta make sure. Okay, yeah, perfect. All right, so you know, this is our anode, this is our anode, this is our cathode. Again, anode, cathode. So pay attention to the orientation. We have the cathode, the negative side, facing this output right here, and then we're gonna have two more, like this, like this. And then we're just going to jump in. We want to make sure that we distinguish we are not connected right there. And we move here to our output. Okay, so this is our full wave rectifier. All right, so as I said, pay attention to the orientation of the diode. So forward bias for the diode is in this direction. That's forward bias. So this is going to be, our current is going to be flowing in this direction at all times, okay? When the alternating current is high on this side, the current flows in this direction. It cannot flow in the opposing direction of the diode. When the current's low or negative, as alternating current does, it alternates between positive and negative, right? So as it's negative and flowing through this side of the circuit, current can only flow still in this direction, okay? As you can see, only in this direction, and it's opposed in this direction. It cannot flow that way. So this is maintained at 0 volts at all times, and this is maintained at our high voltage, okay? So I'll just represent that with a positive. And at this point in time, our output is going to look like this. It's not direct current yet, but we do not perceive a negative voltage anymore. Now the voltage, instead of looking like previously right here, it looked like this. alternating current, although at 18 volts. Here at this part of the circuit, it's going to look like this. And so now the result of that is that we had 60 hertz right here. That's our frequency, 60 hertz. Following the wave rectifier, we have doubled the frequency. So here we're going to have approximately 120 hertz. I'll say it's an approximation, but it might be exact. I'm not really certain. But I do know this to be true. So following the full wave rectifier, we're going to double the frequency. Okay. Which is fine. We're not really worried about the frequency. Okay, it's okay. It's fine. All right, so this is what our circuit is looking like thus far in theory. Now to limit, so to get a more direct response rather than this ripple, okay? Rather than this ripple or this, I'm just trying to think of ways to define it. We still have somewhat of a waveform. To get a more direct line, a straight line, we're going to add in a capacitor here. And now this is something that I'm gonna have to look up. Here, let's give it a little more space, make it look a little nicer. Add a capacitor here. Okay. I guess that's what I could do. Alright, so it's our capacitor C. And now the output at this point is gonna look like this. With here to make it a little better. This is our voltage. Just gonna be direct current. Okay, it's gonna look like that. V, and then here we got, V, negative V. Okay. Getting a little cluttered there, but that's okay. I think everything is still distinguishable. Alright, so I mean that's it. That's literally the AC to DC converter. In its most simple form. Okay, so the one thing I want to do now is that I don't really care about that. The one thing I care about right now is the ripple voltage. Which the capacitor is going to limit. Wait a second. Actually, no, maybe not. So this is something I need to look up because I'm not actually very familiar with. So let's go ahead and do that. Let's go ahead and do a little research. All right, so we're gonna look up the formula for calculating a capacitor's limit on ripple voltage. Maybe this is how we want to word it. The capacitor is used to smooth the output voltage to a specified ripple. Ripple voltage calculator C equals I load divided by 2F V ripple, where for a load current of 1 amp 60 hertz frequency and ripple voltage of 1 volt, the required capacitor is 8.3 millifarads. Damn, that's a big capacitance. Okay, 1 amp frequency and ripple voltage of 1 volt, the required capacitor is 8.3 millifarads. Okay. 1 amp. I could literally just listen to that. So it's telling me that C equals. Okay, so it's telling me that C equals, the capacitance equals the current, the load current, what's called current L, divided by 2 times the frequency times whatever our ripple voltage is. R, we'll call it like that. Okay, so that's what the capacitance will equal. Our ripple voltage. I'm actually not capable of determining the ripple voltage because I don't have an oscilloscope. Right, but there's a method to determine. Let's look that up now, alright? How to determine the ripple voltage. Come on. At the output. Here, I'll change over to this screen. We can look at this stuff together. There we go. Yeah, you can see that. All right, so ripple voltage VPP in volts is calculated by dividing the value of load current in amperes by two times of frequency of AC component in hertz and capacitance in farads. Ripple voltage VPP equals I divided by 2FC. VP equals ripple voltage in volts. Right. So this is, yeah, like as I described before. Oh, that's a half wave. Okay, and that's our ripple. This is the full wave, which we're dealing with right now for diodes to make the full wave rectifier. Right, that's what we drew out. Something similar to this. I guess I should put a resistor there too. No, that's a good idea. That's a really good idea. I wonder what power level of resistor we're gonna require to do something like that. We'll go ahead and draw that in too. I like that. Okay, so looking at this doesn't tell us what I'm looking for. R surge. Peak to peak ripple in DC output voltages. Secondary voltage rating and the line voltage has a frequency of 60 hertz. Ripple factor. Current minus DC current divided by DC VMRS. Not really giving us what we're looking for. Output ripple factor. Calculating ripple voltage. Ripple voltage calculator formula, blah blah blah. Load current, enter frequency, enter capacitance. But I guess I was trying to determine, I guess because I don't... ripple voltage, load, capacitance. But I'm trying to determine the capacitance. Okay, how to measure ripple voltage. Yeah, let's do this. The measurement of the output ripple in switching regulators is a crucial and delicate operation for many reasons. Measuring the unwanted signal requires great care as it is easy to get erroneous readings. Ripple is an unwanted blah blah blah. Ripple is blah 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 blah. Oh, okay. Yeah, RMS. Okay, minus VDC. It's weird that it says, expresses it this way because the RMS value is equivalent to a DC value. I don't know. That's really odd in my perspective. That don't really make any sense. But one thing I'm thinking that I'm capable of doing is here. All right. I think we're going to start putting stuff together. So let's show this one more time. Okay, this is everything we got, we're working with. And, let's see if my transformer still works. Alright, this is what we got here. Is that what I got? What do I got? What rating is this fuse? Open this up and we're going to see. Oh yeah, let me zoom back out now. That make this much better. Properties. Okay. Yeah, okay. Alright, let me pull this out. Oh, wait, let me get out of here. Alright, there. Let's see what rating this fuse is. Okay, so it's a 5 amp fuse. It's a 5 amp fuse. Okay, fantastic. I just want to know what our limit was. Is this off? That's off. Alright, it's plugged in. It's live, so it's live, so we can get fucked up for real. We can get real messed up off this. Okay, I just turned it on, turned it off. I can definitely feel it buzzing. The magnetic field is alternating. The magnetic field is indeed alternating. Okay. Yeah, so we're gonna come off of that, and then we're just gonna plug into a breadboard. I have a linear voltage regulator here, well, circuit, and then I have just the ICs themselves, multiple ICs. So, I'm thinking actually I might just, build the voltage regulator or linear voltage regulator circuit and use this at the output, right? Because we're going to need a voltage regulator regardless, but I also have integrated circuits, but we could just go ahead and build our own. I guess that would make it much more entertaining, but I might save that for another video. So let's come to a conclusion on this AC to DC converter first. Okay, I'm gonna get this stuff out of my way. Alright, fantastic. Got a little more room here. Okay. Yeah, let's get rid of our theory here. Gosh, I gotta be careful with this thing. Just hanging on to it. And do I have a clear breadboard? I don't. I think this is my integrated circuit. Yeah, 7805. That outputs 5 volts. 7805. I don't think you'll be able to see that, but let's put him aside. Okay, we got some resistors here. We'll do something with that. Alright, here's our breadboard. Okay, so let's pull out our capacitors. We're going to use electrolytic capacitors, which means that they... Is this... Wait, actually, is this how we want to go about doing it? I drew it as a ceramic capacitor. But, let's see something. Yeah, okay, we're gonna want an electrolytic capacitor. This, yeah, big. Volts. Okay. Alright, fantastic. Yeah, we're gonna want a big value of capacitance, but we want to make sure that we don't exceed. There's another, why does that happen? Okay. A current limiting resistor. So, I'm definitely going to need to define some values. Okay, the first thing I want to do is I want to get a reading of the output voltage after the full wave rectifier. This is going to give me, you know, a value to work off of. Okay, can you see that? All right, so let's pull a measurement. So after the rectifier, oh yeah, another thing I want to do to determine the ripple voltage is that we're going to pull a measurement in direct current right now. Actually, let's just go ahead and do the... I want to pull a measurement in alternating current, and I want to see what I get. Ooh, that was thunder. That's crazy. It says 200 volts alternating current. That's kind of a lot. And so, I'm trying to remember what's positive, what's negative. Shit. That's positive. Okay, the bottom's positive. Okay. So it's on, it's live. Let's be careful here. I don't get fucked up. Okay, so 6.6 alternating. Wait, it says a little battery on it though. Can you see that? A little battery icon on there. Oh, that's just always on there. So 6.6 alternating. Oh no, that's really interesting. I'm not sure what that's telling me about the ripple voltage. Okay, so we're at 20 volts DC direct current. Let's go ahead and do a little measurement of that. Okay, so 17.7. Okay, so that's what we're going to use. 17.7. Here's my capacitors. Got a big old capacitor. Okay. So, whoa. Oh, yeah, that's after the rectifier. Because there's inevitably some voltage drop across the diodes. I think 0.7 volts is a common voltage drop for diodes. But this is like dependent upon whether they're silicon diode or they're like a germanium diode or stuff like this. I have some germanium diodes right here. Look at that. Fire. They have a bit of a different operation though. I don't know how to explain it. I don't know enough about it. Okay, so at this point, let's call this V. So just got a lot going on here. Yeah, well, we can just say, you know what? All right, let's draw a separate circuit. We don't even need to know all that. We don't even need to know all that. So we're just going to say we have a voltage source here that's going to go to, yeah, literally going to go to, so what? It's just going to become a simple RC circuit? Like this. And we're going to say that this is 17.7 volts. This looks like Garbo, huh? 17.7 volts. Okay, it's gonna look like that. Just call him R and then C. And then, yeah, obviously we'd have some load resistor also. That'd be after the voltage regulator. We'll worry about that in a moment. We're gonna add all that. Okay. I'm just trying to think what's necessary now at this point. Okay, so we have the current limiting resistor, and then that's in series with the capacitor. Now, when I measured the alternating current, or the alternating, the AC voltage, when I measured the AC voltage, it said like approximately 6. Let's look at that again. I feel like this has to give me some insight into the ripple voltage, but I'm not really sure. Not really sure. So I'm just gonna go ahead and plug in value, or I'm just gonna go ahead and plug in some resistor and see what I get. Look at that, 7.1 volts. I mean, that's a crazy ripple voltage. Man, what is that telling me? I wonder what that's really telling me. And I'm pretty sure the multimeter reads in RMS values, so peak to peak is actually greater than that. I wonder what that's really telling me, though. I don't know. Okay, yeah. So the reason I drew this out is because I want to limit the current. So, oh, whoops, I didn't mean to draw like that. So I'm trying to think, what value do we want here? Eventually that's gonna look like an open. Everything would come across there, but in the beginning, this is going to establish, I guess, our delay. I don't really care about that. The voltage here. 17 volts. What other kind of but I'm not going to use these, or perhaps I will. Okay, so what? I would require that. But it's not going to be 17 volts. That's not really necessary. I guess that resistor isn't necessary. Okay. I don't know, it's just becoming fun. It's becoming a lot more simpler than I thought. Alright, that's fine. So let's go ahead and just gonna go ahead and choose a value of a capacitor. So let's do like we want a pretty high capacitance, maybe 1,000 microfarads, which is 1 millifarad. That's rated for 16 volts. That's rated for 10. That ain't enough. You exceed the voltage rating of a capacitor and it's gonna explode. I've done it before. I've done it plenty of times. That's 470 microfarads. 10 volts, 16 volts, 16 volts, 50 volts. You know, we could do a voltage divider and step this down even more. Let me think about what we want to do right now. But cool. Hey, I appreciate you guys joining the stream, tuning in and shit, man. I've been pumping out some videos, so you can go to my profile, see my videos and shit like that. Honestly, I don't know why there's not more people in here. Man, having a difficult time getting some reach, huh? Having a real difficult time obtaining some reach. Would have 0 viewers on YouTube. Right? 0 viewers on YouTube. Let me even make sure the YouTube stream's popping, like actually working. Because I never went to see. Yeah, it is. Having a real difficult time obtaining some reach. Bruh, I just turned down my volume so you guys want to hear it. That's whack. Like and subscribe. But yeah, okay, I'm thinking we could use a voltage divider to step this down. Because what do we really want for our output current? Or output voltage? I kind of want it all to stay the same, but my capacitor ratings aren't that high. I only have a 100 microfarad capacitor rated for 50 volts. And that's not very good. I want to use the 1000 microfarad capacitor. Yeah. 1000 microfarad capacitor, but it's only rated for 16 volts, which is really pushing it close. And then if we're to use a voltage divider, we're going to be burning we're probably going to need, if we're using a voltage divider. So like, okay, let's just theorize something. So what do we want? Because it's going to require a high power resistor. You know, we're talking about like 1 watt. I don't know. I don't even know. Maybe it could be 5 watts. Let's see. And plus it's going to get really hot. Like, that's such a waste of power. I don't really want to do that. But it might come down to this. So we have 17.7 volts. And then let's just theorize for a moment and think about what our voltage divider is going to require. Like this. What do we want? What do we want? I guess we need to get lower than 16 volts. You know, there's this phenomena that sometimes the capacitor voltage exceeds the input voltage. So, you know, we could be applying 17 volts and getting out and having perceiving like 20 volts across the capacitor, and so it's not going to be a good thing. So I'm trying to think. If we had a voltage divider here, doesn't need to be much. Doesn't need a bunch, but if then that means there's going to be a bunch across here. We can go down to 13 volts. 13. Let's do that. Let's drop down to 13 volts, and then we'll do a 12 volt regulator. Okay, so that means we're going to have 4.7 here, and we're going to take the output here. Yeah, so 4.7 drop, and we want 13 volts here. 13 volts. So if we want 4.7, 4.7. Okay. So R1, or we'll call this R1, R2. Okay. Let's get this shit out of the way for a moment. I'm not even going to zoom in. Actually, yeah, I will. I want you to be able to see it good. Okay, good enough. Alright, okay. Okay, so if we have a 4.7 drop across this resistor, I think I'll only have half watt resistors. I do actually have some, I do have higher power resistors, but I have a lot of half watts. So let's see what this looks like. So the equation for power is power equals, and we know our voltage drop equals V squared divided by R. Okay, we know our power equal, okay, so this is going to go to 0.5 watts equals, we have a 4.7 voltage drop across that capacitor divided by R. So we're going to have R equals 4.7 squared divided by 0.5 watts. Let's see what this resistance value is. So 4.7 squared divided by 0.5. 44.18. Okay, so that's at a maximum. And so if that's the case, then we have 4.7 volts divided by that. And that's, yeah, 100 milliamps. The resistance of that will change. Actually, no, it won't. Not if I have that. 100 milliamps. I kind of want more than that, though. But then we're going to exceed the power rating. Okay, maybe that's my issue, is that I'm not going to be able to do this with a half watt resistor. So let's look at the value of what other values do I have for resistors for the higher power? 10 watts there. Definitely don't want that now. 4.7 volts. That means I'm gonna need something like that. 12 ohm. Do I have 5 ohms? 12 ohm wire round resistor, 10 watts, 50 ohms. I don't think I do. 10 watt. Oh, I got a 6 ohm. Wait, so what if we did 4.7 divided by 6? Okay, that's closer to 1 amp. Yeah, and then we're gonna multiply that by 4.7 because that's our current multiplied by our voltage, and that's gonna give us 3.68 watts. Watch, these resistors are rated for 10 watts at 6 ohms. So that's fine, that's what we'll do then. Okay, so if we have 4.7, that's gonna be R1. Get rid of this, it's no longer applicable. Okay, so we're gonna say that R1 equals 6 ohms with a 4.7 voltage drop, 4.7 voltage drop, or well, 4.7 volts divided by 6 ohms equals our current, which is 0.7833. 0.7833. That's fine. Okay, that's 783 milliamps. All right. Okay, so if that's the case, we're going to have to figure out the second value, 17 volts. Wait, this equals, we want 13 volts at the output, multiplied by R2 divided by 6 plus R2, multiplied by that side. What, 6 times 13, that's 60. 6 times, that's 8, that's 78. Plus 13 R2 equals 17.7 R2. 17.7 minus, that's going to be 78, equals 4.7 R2. Yeah, right, 17 points. Yeah, that's our, and that's our 4.7, and then 78 divided by 4.7, okay, 16 ohms, R2. Okay, so which, I have a 12, wait, those are two, oh, I have 2 ohm resistors, nice. Oh, 12, no, those are 12. 6 ohm, 12, I need 16, what is this? 100 ohm. Okay, and so 16 ohms, wait, let's, 16.5, whatever, we'll round it to 17, we'll say more like 17, not that that's gonna matter, but 17 ohms. So if we have 13 volts divided by 17 ohms, it's going to give us, oh, right, because they both perceive the same amount of current because they're in series. Makes sense, makes 100% ton of sense. Okay, right, and then, oh man, but that's going to be a much higher power rating. That times 13. Whoo! It's almost 10 watts. That is 10 watts. You can consider it to be 10. I got 20 watts for 12 ohms. I could do 12 in series with, what are these rated for? 10, 6. What's that going to make our resistance? 12, 6, that'd be 18. That's pretty close. That's good. Wait, so what if we did 13 divided by 18? 0.722, and then times, yeah, 13. I'm gonna really be pushing the limits of those. It might be okay though. It just might be okay. Damn, that's a lot of, it's gonna get hot though. It's gonna get hot. I almost don't want to do it, but let's do it, whatever. Okay, so if that's the case, okay, so we're gonna use R1 equals, actually we're going to have to define that again. R2 equals 18 ohms because this is all we have. Okay, so we're going to decrease the current a little bit more. So if that's the case, we have 13, we want 13 equals, we're going to solve for R1 now. 13 divided by 17.7, and then we're going to multiply by that, so that's going to become 0.734 times R1 plus R2, which is, we want 13, oh wait, we want to take this times 18, and that's going to equal 13.22 equals, no, we already got rid of that, equals our, oh yeah, equals 18. So 18 minus that, and then divided by 0.734, and that's going to give us R1 equals 6.511. And what we say it was before, we just said 6. R1 equals 6. Wait, this isn't what we want to, shit, this isn't what we want to do. Okay. No, we just want to see the output voltage now. So 17.7 times 18 divided by 18 plus 6. 13.275. Okay. So that's our output voltage across R2. That's what it would be. But, what the hell? What the hell? 13.275. So that divided by 18 times, or no. Yeah, that's our voltage divided by the ohms. 18 ohms times 13.275. That's okay. And then this divided by, no, that's not gonna be applicable. That's not applicable. We just say 17.7. That would be applicable. Shit. Shit, that is applicable. Okay, so we can do, oh man, we can do a bit of a workaround. You know, if you put things in parallel, this is going to split the current, and then this is therefore going to, wait, but if you did that too, that would change the voltage. You know, we might be okay. Okay. I think we're going to be alright. So let's go ahead and start plugging stuff in. I ain't gonna lie, this isn't going as well as I wanted it to, because I'm not very like linear in my way that I'm operating right now. I'm just kind of doing things all mumbo, like just all over the place. But that's okay, because I made the decision that I was gonna There's a fucking, what is that? Is that another mosquito? Bro, ain't no way it is. Been eating me up, dude. Like sneak attack too. I don't even feel him on me. Dude bit my face, I think. I absolutely, that actually, I might crash out over that, bruv. That shit pisses me off so bad. I absolutely hate the blood-sucking mosquitoes. Like, whoa, like, my lord God, what is this? Like, why would he even create such an abomination, the mosquito? I just simply do not understand, okay? He's over here flying around my table. I tried killing one of them yesterday, and I couldn't. I simply could not catch him. I guess he was too fast. My perception was all weird because of how small he was. I thought he was closer when he really wasn't. And so I went and had to get the Lysol, and then I did some chemical warfare on that little bit. You know what I mean? Pulled some chemical warfare and took him out with the aerosol. But man, he was really annoying the shit out of me. He kept biting me, bro. He just kept getting me, and I could not catch him. But the aerosol did. The Lysol got his ass. I guarantee you that. All right, let's get this back over here. Let's start plugging stuff in. No, let's just see if it works. Like, whatever. Alright, so this is our 12 ohm resistor rated for 20 watts. Far exceeds what we need. These things are big. Check it out, it's pretty big. Can you see the rating right there? 12 ohms. What we do, here's our breadboard. This allows you to do prototypes easily. Look, this thing takes up the entirety of my breadboard almost. That's not good. Okay, so we're gonna go like this. Alright, he's going to be in series with our 6 ohm resistor rated. Oh wait, actually we need multiple. I haven't even opened these yet. Crazy. Brand new. Man, get your friends in here. Tell some people. Tell your family. I don't know. I don't even got any viewers. I appreciate y'all that are in here. You guys are the best. You guys are the best in the entire world. Fucking love you guys. Okay? I really appreciate you being here, tuning in. I don't know. We're just like exploring some electronics. Right now we're building the AC to DC converter. You know, it's very important in all sorts of electronics. And, you know, we're just getting some insight into how technology operates. We're looking at the engineering, the physics. We're looking at the science behind it. And I don't know, it's a beautiful thing. Maybe it's not applicable to your life, but hopefully it's entertaining. It's definitely going to make you a more well-rounded individual, you know, knowing these things. You know, perhaps you go out on a date with some girl, or I don't know if you go out with some guy like that. You have a little bit of knowledge you could spit. A little bit of knowledge to get their interest up, you know. Now they're all interested in you and shit. Like, oh, I wonder what else they know. Yeah, so right now, not only am I teaching you science, physics, mathematics, but I'm also teaching you game. Alright, how to be a player. Alright. Yeah. Fuck with that. Alright, this is really bad design. So those two, and then we also have 6 ohm again. Okay, but he's gonna have a 4.7 volt drop across him. I guess so with that too, and then that should have the remaining, right? So 4.7. That'll have 8.3 across it. 8.3 divided by 12. Yeah. 69, okay. And then I don't know, maybe I feel like there's mosquitoes around me, because I got like what do you call it, heebie-jeebies. But I really did feel something. I thought there was one on me. Alright. And then this really sucks. This is a tiny ass breadboard. Oh man. Alright. That's a resistor network. Okay, so now we're just going to plug in this capacitor, which we're definitely going to have no trouble with as far as, because we want about 13 volts, and so we should be able to do the 1000 microfarad capacitor rated for 16 volts. Let's see how this goes. Maybe you'll get to see 1000 rated for 16, yeah. Yeah. An important thing of capacitors is, like, I'm not really touching any of the electrodes of it, but you just gotta make sure that it is discharged. You know, capacitors, they store charge in an electric field, so if you're not careful, it could shock you easily with the stored charge it contains. There's some, like, parasitic resistance that it will leak out over time. Or, like, leakage resistance. I don't know what it's considered, really, but, okay, so this will just easily go like this. So we're putting him in... No, we want him in series with our, yeah, we want him in series with our resistors. And we're gonna take the output across there. So that's gonna be our ground. Okay, so let's pull out some wires right here. Like this. I'll give it a little tilt so you can kind of see it better. Alright, so we're gonna keep that wire shorter, even shorter, that's better. Okay, so this is going to be our ground, or well, it's gonna be our reference point, I guess, yeah, or this will be the ground, the whole ground. Right here, so we're gonna plug in, yeah, because we want to take it across this capacitor, or these, right? This is how we're gonna do it. This is our output across these. Wait, actually, so I do want to go from here, because that's connected there. Yeah, from here to here. Yes, okay, and then this is going to be our ground. I'll just do that in a moment, and then that's going to be our input from our rectifier. Okay. No, that should be good. That should be good. So this is our input from our rectifier, and this is where we're going to ground everything. Right here. Just like that. And guys, looking kind of shitty, but this is all simple for simplicity. You know, perhaps I'll plan it out and do a better, more succinct video. And actually go into better details. I just got to do a little research myself, but I'm just incredibly busy, so it's just tough. Okay, I just want to make sure, think about this. Yep, we have our voltage divider right there, and then our capacitor is across the output of our R2. Yeah, after that, it's going to go like that. Okay, and then that's connected to there and to there, and that's the total. Alright, let's try. Let's plug it in. With our alligator clips right here. I actually need more of these. You know what? I'm just gonna skip these wires. I'm gonna plug into our. I think it's gonna be a lot better. Okay, this is our negative, or no, that's our positive side. Yes, we're gonna go positive here. Oh man, that motherfucker ain't on it, is it? Okay, no, it's not. Scary. Alright, just like that. I don't want to be touching anything. Just like that, and this is our ground. Our negative. Oh yeah, actually, let's do the same here. Get rid of that wire. I'm just going to plug right here. Yeah, that's a lot better. And boom. Alright, so I'm just going to turn it on and see if the capacitor blows up, and then I'll take some values. Okay, it seems to be working. And then you can feel the heat dissipation on the resistors. I probably didn't run it long enough for it to really get too warm, but it will start to warm up. Okay, so let's take the output across the capacitor, or yeah, across the capacitor. I think this is what we want. Yeah, okay. What the? What the hell? What am I measuring? Oh, that's why. Measuring in that. Okay, flip it over to DC, obviously, duh. Okay, now let's measure. Okay, 13.34. So it's really close to our theorized value of 2.5 or 13 point. What was it even? That's really close to our theorized value of. Did I not write it down? Meh, whatever. Okay. But there you go. Okay, so now we've just want to feel these, see if they getting hot. Definitely warming up. Ain't getting that hot though. That one looks like it's burnt. Yeah, burnt. Oh fuck. Oh shit. But yeah, there's that. Okay, so now we can take the output across this capacitor and we can put this into a voltage regulator, which we're gonna establish. Yeah, no, okay, so our current hasn't exceeded 1 amp. It shouldn't, according to our theory. I could hook up the ammeter, but I'm not going to do that. So now we have L7812. This is our voltage regulator, L7812. So we're going to go ahead and take one of these. We're going to plug him in, and we're going to get a constant voltage of 12 volts. 812, that's down here. Oh my goodness, I can't get him. Yep, L7812 voltage regulator. Making sure that is off. Okay. Oh man, I wonder what these little wires are rated for, because I think we're gonna be right. Actually, it won't. Okay, so now we're gonna plug him in like this. Maybe you can see it then. Yeah, these are a bit concerning, but fuck it, let's do it. So this is our ground, which is gonna go to the center pin of the voltage regulator. And this is our reference point, or our positive voltage, which is gonna go to the first pin of the regulator. Like this. Like that, and then our output, I just kind of want to, I need to get a wire in there to distinguish and also to use, or to hook up to, and that's going to be our output is the third. Okay, so just like that. Okay, and that's our voltage regulator there. Okay, so let's get our power supply, or well, this entire thing is the power supply. We're making a power supply, so we want him hooked up again to here. Okay, we want him hooked up to, ooh, is the breadboard hot? We want him grounded right here. Yes, right here. Grounded, that is our ground, right? That's our positive, this is our ground. Okay, so that's all good, just like that. Okay, I want to make sure I got the voltage regulator hooked up properly. Looking good. That's across, and then that's where I want to take the reference from. Yes. Okay, that seems to be good. Alright, we're going to try to get him to, that's our ground. We're going to get him to sit right there. There, that should work. And then we're going to reference this little wire right here. So as of right now, I got nothing. Okay, here, I can't see shit. I want to see how hot those are getting. I wonder how hot he's gonna get. It's icy. I don't want to, Man, it's a bit of a mess, huh? Okay, you can see that too? Alright, turned on again. Oh, 11.75. 11.75, so that was good. Okay, there you go. 11.75 at the output of our voltage regulator. Yeah, those resistors are starting to get hot now. I knew they would, because we're really close to the power rating. We're really close. Okay, so an output of 11.75. I want to hook up a load, but I'm trying to think, what should we hook up? I don't know what requires approximately 12 volts at less than 1 amp. Give me something. Yeah, this is 9 volts. I'm pretty sure this motor is rated for 9 volts. Fuck it though, let's hook it up and see what happens. Alright, let's do it. I really want to know the current that's going to be drawn, but whatever. Alright, let's hook up this motor and see what happens, just for fun. Ooh, okay, it's working really hard. I'm probably gonna burn the windings if I continue to run it for long periods of time. Here, this can keep my resistors cool. We'll use the resistors to power the fan, which will keep the resistors cool. Woo! That baby running overtime. Really pushing the limits there of that motor. Okay, I kind of want to do a reading. I want to read the voltage across this thing as we're running it. Shit, I don't really have a good way to do this. I got a really shitty setup right here. Just want to get some kind of reading. Oh, it's getting 6 though. It's getting 6 volts. Is it getting hot? It's really not. It's not getting hot. That'd be like a quantitative. Oh, it's kind of coming out here. Alright, so yeah, you can see that we have our resistor circuit here. This is to divide the voltage because we don't have the voltage. Divide the voltage because we don't have any capacitors that are rated for greater than. We don't have any large values of we don't have any capacitors with a large value of capacitance rated for anything above 16 volts. So therefore, I use these resistors to divide the voltage into 4.7 volts and then 13 point something volts respectively. And then across the two resistors that are outputting 13 volts, we put a capacitor in parallel. This is to limit the ripple voltage, or like get rid of the ripple voltage. We don't want that. We want a direct current, a constant. And then we put that output after the capacitor into the voltage regulator, which is the L7812. And the last 2 digits, the 12, is what is the rating of the output voltage. So that means 7812. That means we're going to get a 12 volt output, a constant 12 volt output. And then now we went ahead and plugged in a load, which is this DC motor right here. And you can see, and I measure across it, and the motor is getting 7 volts, which is interesting. Yeah, because obviously it itself in the coils of its winding has some resistance and stuff like that, so that's going to change the output of our voltage with the load. Yeah, but I thought that should be constant. Oh, yeah. and these are getting really hot. All right, well, there you go. I don't know, that's all I had to do today. Maybe it wasn't like a very organized video. Definitely could have done better with that. But I think we still had a good time. I'm really happy you guys were here with me. I really appreciate it, for real. Like the video if you would. Give me some more engagement. Subscribe or follow me, for real, because I be posting videos. I might edit this one and post this one too, although I feel like it wasn't organized well enough. So I just want to get on the live today and share this with you guys. But for real, I really appreciate you being here, and I hope you have a great rest